Yeah. So propositional logic, the recap, what we summary of what we discussed last time. So what we introduced was the syntax as well as mainly the semantics, and especially this we defined with some detail the semantic entailment, that is the double turnstile thing, the element, which was satisfiable. So it was defined as given a model, which for the propositional logic case will be just truth value assignments for all the variables in the formula. Given that, turnstile defines the semantics by defining precisely saying when a formula is true under that truth value assignment. So, for example, this for these assignments, this particular formula holds. That is, it is true. And the way it is defined, as you saw, was by going down the structure, the tree structure of the formula. So one logic connective at a time, going down, and for each of the logic connective, there was a way that the semantic rules defined how to interpret the meaning of the formula in terms of the truth value for the sub-formulas. Okay, so this entailment, semantic entailment operator, it can also be extended. Okay, so where it is, I introduced it for a particular model, can also be extended to a set of formulas in the precondition, that is before the turnstile. What this means, that a bunch of formulas, psi1, psi2 in this case, as an example, semantically entails phi, which means, what that means is, for every model M, that is for every value assignments for the variables, if, oh, I'm sorry, there is a mistake here. So if psi1 is true in that model and psi2 is true in that model, then so is phi. Please ignore the phi's here. So, yeah, so this is, the semantic entailment, assuming certain formulas hold. So validity is, say that a formula is valid if it is true for every model. It is unsatisfiable if it is there's no model for which it is true. And the way we have defined the semantics, a formula is valid if and only if its a negation is not valid. Okay, so there is a parallel in all logics. There is a parallel to semantic entailment. Okay, and that's called deductive entailment, denoted by a single turnstile, which this should be read as psi1, psi2, phi, the formula phi, logically can be derived as a logical consequence, can be deduced as a logical consequence of a set of formulas, in this case psi1 and psi2. We already saw in the motivation example of an instance of this kind of deductive entailment, saying that knob B follows as a consequence of these three. In this case, I've done a conjunction. You could say there are three psis here: psi1, psi2, not C, and psi3. So when I say psi1, psi2, it really means that, assuming that all of them are true, that is a conjunction with true, then the conclusion, which is written following the turnstile, can be deduced. And this, obviously, that can be checked using semantic. You can use semantic entailment to also check that phi holds, but deductive entailment is deduced. The deduction here is done by constructing a proof as a series of a sequence of application of inference rules belonging to a system of a system that's a proof system. Okay, there can be several proof. There are different versions of proof systems that have been proposed in literature on logic. Natural deduction is one such. Sequent calculus is one, and resolution principle, inference rules based on resolution principle, is also another one. And this is something that I will briefly introduce in my next slide. Okay, because this resolution principle, the inference rules that make the resolution principle, are the basis for SAT solvers and SMT solvers. So once you have two kinds of things, as I told you, that you can always check that phi, a consequent phi follows or holds, assuming that psi1 and psi2 using semantic entailment. And that's pretty much, in the case of propositional logic, it pretty much boils down to checking, validity checking boils down to checking the truth value of phi for all possible models, which is for all possible value assignments. Okay, and you can follow the rules of semantic entailment that we already saw to do that. And that pretty much boils down to, in the case of propositional logic, constructing a truth table for checking the validity of a formula. Okay, so if there are n variables, then you will have to do that. You will have 2 to the n different possible things that you have to check for. The idea of deductive, the motivation for having a deductive system is so that you will get shorter proofs, okay, using these inference rules. Okay, so that is the motivation, and also you could then automate these application of these inference rules, because these inference rules, as we will see, is defined in a very symbolic or mechanical way, and that can be instantiated to implement, to automate it. Okay, so once you have these two different ways, this is model theoretic. Semantic entailment is based on enumerating, defining the truth value of a formula based on by looking at all the models, whereas here you apply inference rules. Okay, once you have these two kinds of things, then you can talk about soundness. You might have heard of that given a proof system, a deductive system, there are two notions, very fundamental notions in logic of the attribute of the proof system. One is soundness, and the other one is completeness. Okay, this kind of relates the semantic entailment with the deductive entailment. What does sound, when we say that a proof system is sound, we expect every proof system to be sound. If you using the inference rules, you can derive phi to be as a logical consequence of a bunch of assumptions, psi1, psi2, and so on. Then it should be, it should also hold as per the semantics, as per the definition of semantic entailment. Okay, so that this means that your inference rules are, are correct. Okay, in some sense they are sound in things, so they do not deduce something which is false as per the semantics, and that's what soundness.
Sir,
Yes.
I have a sir. I forgot what does this like sign mean?
Which
This
sign?
in that soundness sign, the symbol with like straight line and then a perpendicular one, but only single, not double.
Yeah, this is the single turn style. Okay, you mean this one, correct? Single
Yes.
turn style. Yeah. So that we will define. Okay. Here, I mean, I will show in the next slide some details of that. But for now, assume that you have a set of inference rules. I haven't actually shown you inference rules, and the notion of proof. Okay. So whereas here you are checking, for all models, correct? In the semantic entailment. So
Yeah.
I have defined here the deductive entailment as derivation of a conclusion from a set of assumptions, psi1, psi2, etc., through an application of a series of instantiations of the inference rules of a proof system. Okay, so that's how I defined it. Yeah, and that is and this series of application of inference rules is what makes up a proof for phi from psi1, psi2. I haven't shown that. Okay, so for now, assume that that is another way to deduce. Okay? Yeah.
What is a symbol called? Single turn.
Or single turn style is I call deductive entailment, or you could just say phi is deducible as a logical consequence of psi1, psi2, etc. Okay.
Okay. And what is the second symbol called? Double turn something.
Style that you can call as I say semantic entailment is what is the thing that I've given here. This should be read as psi1, psi2, assuming psi1, psi2 hold in a particular, for every model for which psi1, psi2, etc. hold, for every model in which psi1, psi2, etc. are true, so is phi. Okay, so just read it that way. Yeah. So for succinctness, we are just using this double turn style. Okay, and it says that for every model in which all the preconditions, okay, psi's hold, that for every model M for which all these holds, so does phi. Okay, that's how we should read it. Yeah. So I mean, SMT solvers, what they do is they construct proofs. Okay, they are SMT solvers and SAT solvers. They are efficient ways of constructing proofs using certain set of inference rules. Okay, they are constructing proofs based on using certain proof system, and they use a lot of heuristics, etc., to make that proof construction process efficient, rather than enumerating all models, okay, for checking validity. Okay, so but when you're talking about this soundness and completeness, they establish certain desirable attributes of the underlying algorithms, okay, that make up an SMT solver. So soundness ensures that whenever you conclude using, whenever you deduce a conclusion logically using the proof system, that indeed it is correct as per the meaning assigned to the formulas. And completeness ensures the reverse. Okay, that every formula phi that holds, that can be that holds, assuming in psi1, psi2, etc. hold, that you're able to derive. The proof system is strong enough, is adequate, is complete enough to then derive every such conclusion which is true as per the semantics, okay, of the thing, so that you can be sure that, that everything you can use, you can deduce that is true. Yeah. Yes. Was there a question?
Yeah. So the variable set in propositional logic, is it like finite always?
Yeah, a formula, all these things are, we assume that the formulas are finite. Okay.
Okay.
So, you can have infinite number of formulas that you can construct, but each of them is finite. Yes. Yeah.
Using
which means that the number of variables in it will also be finite. That is, in this case, preposition. Yeah.
Just to tackle that problem, that's where first order logic comes in, right? If I'm not wrong, just.
That's right. So when you go to first order logic, as we will see, those here, since this is just propositional variables, and we allow, and each propositional variable can only take two truth values, true and false, and you have a whole, finite number of variables. So all your models are finite. Okay. So whereas when you move to predicate, first order predicate logic, as you will see, you can have your variables range over infinite domains, and your models will be a lot more complicated. Okay, and your domains can be infinite as well. Yeah. Okay. So these are two notions which, using the resolution principle, I will quickly, in the next two slides, demonstrate what it means to construct proofs. Okay, and we will revisit the resolution principle when we talk more about some of the internals of SAT solvers and SMT solvers. Any questions here? Okay, if there are none, I will move. Yeah, so this is the resolution, one of the rules of resolution. So I'm assuming the resolution works, this proof system works, assuming that your formulas are in conjunctive normal forms. Okay, I showed you what a conjunctive normal form is. If that is not clear to someone, you should ask. It is a conjunctive normal form is a formula in proposition logic, which is a conjunction of a set of clauses where every clause is a disjunction, an or-ing of either a literal, where a literal is either a propositional variable or its negation. Okay, so every Boolean function can be expressed as in a conjunctive normal form. Okay, so and the inference rules that I'm going to be introducing, this proof system that I'm introducing, which will have three inference rules. That's what make up the resolution principle. Assume that your formulas that you start with are in conjunctive normal form, and one can always convert any Boolean formula in propositional logic in this fashion. Okay, so is that clear? So no one has any doubts on conjunctive normal form. Okay, so what is resolution? So given two non-empty clauses, okay, so clause C1 and C2, which have one literal, which has one literal with opposite polarity, means that, for example, here, see at least one literal, one or more literal, okay, at least one literal with opposite polarity, which means that the literal appears positively, that is, as the positive literal, unnegated but negated in the other. Then it says you can resolve these two clauses. That's what this operation is, to derive a conclusion, okay? What is called a resolvent, that is, which eliminates this 2C and C bar, and it takes the union of the rest of the literals in the two clauses. So we say this operation as resolution. We say that this operation is resolving two clauses C1 and C2 in the variable C, and the result you get, which is the union of all the rest of the literals in the two clauses, as the resolvent. Okay, this operation, a simple operation which can be automated, is what is called resolution, binary, to be specific, binary resolution. And there are two more rules. Okay, so if there is unit clauses A, A hat, okay, the two clauses are unit and they are of opposite polarity, then you derive something called, you derive an empty clause, which is denoted as contradiction. Okay, because both A and not A cannot be true at the same time. So this derives a contradiction. And other instances that if you have two clauses which are which are of this fashion, A or B, that is clauses of size 2, and this results in the resolvent. If you apply this inference, the resolution inference rule above that I've shown above, then what you get, the resolvent will be A or A bar, correct? And that is a tautology, and therefore that derives true. Okay. So, but on all other pairs of clauses which have more number of literals, you can do this. You can apply this inference rule to basically what this does is it eliminates one, merges the rest of things, and it eliminates one conflicting pair of literals in two clauses. Okay. So I will introduce a notion that two formulas phi1 and phi2 are satisfiable. Okay, this is a notion. So we've already defined what satisfiability means of a formula. Two formulas, phi1 and phi2, are said to be equally satisfiable if phi1 is satisfiable if and only if, this should be phi2, there is a typo here. Phi1 is satisfiable if and only if phi2 is satisfiable, which means that if phi1 is satisfiable, so is phi2, and vice versa. If phi1 is unsatisfiable, then so is phi2. Phi2 is also unsatisfiable. Okay. Given this, what this resolution inference rule guarantees is that the resolvent that you get by applying the resolution operation on this complementing literals is equisat with R. As actually, you can actually say more. The resolvent is always implied. It follows as a consequence of C1 and C2. You can see why this is the case, because suppose C1 and C2 is satisfiable. Okay, we have to show that if C1 and C2 is satisfiable, so is R. Okay, so what is the way to satisfy C1 and C2? Anyone?
Like anything other than C is true.
Suppose anything other than C is true. So you have to satisfy both the clauses. correct? So
Yeah, and so
if you don't want to, if you choose to satisfy A1, this clause can be satisfied by, picking any of the AIs, okay?
yeah,
And of course,
and
you will have to pick a BI also, and correct, a BJ, some other BJ, because both of them have to satisfy, yeah? So that is one way to satisfy. And by picking an AI here and a BJ here to be that literal to be true, okay? But then, so will R be satisfied, correct? Because the same assignment satisfies the same as well. Now, if your satisfying assignment for C1 and C2 is one in which you choose C to be true here, and all the rest of the A's are false, say, then, of course, then C bar cannot be, you cannot make C2 satisfy C2 because C bar will be false. So you'll have to have one of the BIs, make one of the literal BIs to be true. In which case, that BI will be, so in which case also the resolvent will be true, correct? Because the moment you have to have one of the B, if you make C1 satisfied by picking C to be one and all the rest, you have to have one of the B's to be true, in which case you can make, you can always, R will be satisfied as well, yeah? So that's why I think. Yes. So if C1 and C2 itself is unsatisfiable, see, that can happen only when you have something like this, okay? When both clauses are unit. Because if you have, at least, two literals, then you can always make, a pair of clauses satisfied. And that's when then the resolvent would be contradiction, okay? So that is the thing, the soundness of this, I say that this resolution inference rule is sound because what it derives as a resolvent is always implied by C1 and C2, okay? So just, here the idea is not for you to make you understand all the nitty-gritties of resolution and so on, but just to give you an idea of what a proof is, what inference rules is. Inference rules, they actually always go from some, premises like this, which is given above the horizontal line, to something which you derive as a conclusion, which is written below the horizontal line, okay? And so this single resolution principle, which was actually introduced by Robinson, logician Robinson in 1965, is he showed that it was complete for deducing that any propositional formula is unsatisfiable, okay? In the following sense, for any formula phi in CNF, phi is unsat. For any formula phi, which is expressed as a set of clauses, phi is unsat if and only if you can derive contradiction, which is denoted as bottom, by means of a resolution proof. And the resolution proof is nothing but a sequence of series of instantiations of one of these roots, okay? Application of one of these three forms of resolution inference rules, okay? So it's in that sense, it's same. So it is a complete procedure, proof system for deriving, for proving validity. As a matter of fact, you could, because a formula is valid if and only if it is negation is unsat. If you want to prove something to be valid, you just take the negation convert it to its CNF, and then you apply a series of steps of resolution, and it guarantees that if you derive unsat, then you know that the original formula is valid. Okay. So once you have such proof systems, then you could use this as a basis for constructing automated decision procedures, which is what SAT and SMT solvers do. Any questions here? So I will show you an example in the next slide. Okay, that should hopefully. So remember that this problem that this formula that I used in the motivation slide, which I claimed that a set of premises, three set of statements, declarative statements, from that we could conclude not of B. I'll show a proof of this using resolution inference rules. So in order to prove this, you have to show that this implies not of B. Okay, that is with the premise, and then you take the negation of the conclusion that the conjunction of all those things should be unsatisfiable. All I've done here is I have converted this into an implication. Okay, that because I can, because as I said in propositional logic, this logical deduction, which is denoted by the singleton style, has the same meaning as replacing it with implication. So what I've done is taken the negation of that. So in order to deduce this thing, when I take the negation of the conclusion, conjoin that with the all the premises, and get and now I have to show, if I show that it is unsat, then I've shown the validity of that original implication, or in other words, I've shown that not B follows as a logical consequence of these three premises. So this one, as of now, is not in conjunctive normal form because of this implication, right? The first conjunct here is not in clause. It's not a clause, okay, which you'll have to convert into a clause. That you can do by converting an implication. A capital A, any formula phi implies psi is not phi or psi, okay, which is what I've done. So here, to convert this into a clause, okay. So taking the negation of A and B using the Morgan law, I hope you know that. That is, the negation of A and B will become not A or not B or C. Okay, so I converted that into a clause. The other two are already in clausal form because they have a single literal, not C and A. And to that, I have also added B. So far, clear? Any questions? Okay, so we have to prove that this is unsat. So here is, so each V here denotes an application of the an instantiation of the resolution inference rule. So here, there's clause C1 and C2. So has C in with different polarity in it. So I can resolve these two clauses on C to get then the resolvent will be just the remaining union of remaining literals. In this case, C2 does not have any other literal other than C bar, and therefore I get A bar or B bar. Okay, then I do the same thing. Then I can apply a resolution for this new thing that I can add this resolvent, because as I know that, I already proved that the resolvent is follows as is an implied, as an implication. It's an implied. It's follows as it's an implied formula. That is C1 and C2 indeed implies this. Okay? Therefore, they can safely, soundly add it, okay? Because it's already a conclusion of that. So that's then I can now resolve N1 and C3 on A to get B bar, after which then N2 and C4 will result in a contradiction, proving that this set of clauses, or the conjunction of these clauses, is unsatisfiable, and therefore the original formula is valid, okay, or that is that not B follows as a conclusion, logical conclusion of this. And you see that this required only 3 resolution steps to prove, as opposed to that, in this case, because there are only finitely many variables, you could have used the truth table way. You could have used semantic entailment in this case, because there are only finite many variables, as someone observed. So, but then in order to check the validity of that, you would have had to enumerate 2 to the 3, 8 different possible value assignments, okay, which does not scale, okay. So that's why that is where this doing it in by using constructing proofs will be more efficient in some cases, because you have to have methods of constructing very small proofs, okay? And that is the real the crux of what SAT solvers do. Okay, so here is a SAT proof. Okay, so if I instead of adding the negation of the conclusion, which is what I've done here, if I added the not B itself, that is indeed that set of clauses is not unsat. Okay, and therefore you will see that you will not be able to derive a contradiction. You will end up, you can apply these these resolution principles, because there are only finitely many clauses with finitely many literals. You can only apply them finitely many number of times. You can apply resolution without constructing new resolvers. So that procedure eventually terminates. If that terminates without producing bottom, that is contradiction, then you know that it is the original formula is not unsat. Okay, in that case, it is indeed satisfiable, and from that proof, you can actually extract a satisfying assignment, which is more efficient. Okay, so this is what. So I gave you an example of a proof system, which is based on resolution and what it means to construct a proof. Okay, and I hope I have motivated as to why doing it this way is better, more efficient. Okay, provided that you can have the ability to construct. So all these SAT solvers, SMT solvers do are they search. They use a certain proof system. As a matter of fact, in SAT solvers case, they use resolution to search for the shortest unsat proof for any formula. So it uses a whole bunch of heuristic as well as learning techniques, okay, to based on certain patterns, recognizing certain patterns, etc., to make the search of these resolution proofs very efficient. Okay, and that's what it does. And this business of, these attributes that I introduced of soundness and completeness are very important, to ensure that your algorithms that go into making a SAT solvers are doing the correct thing. Okay, and they're not coming. They don't produce incorrect, unsound conclusions. Okay, so any questions here before I move on to introducing the predicate logic, which is what is the basis of SMT.
Sir, like this looks like it should be like faster than exponential.
It should be what?
Unset proofs should be faster, should not be exponential, I think.
Uh,
And time.
no. See, the thing is, this problem of Boolean satisfiability is NP complete. Okay.
Yes.
So in the worst case, it can be exponential. There are some problems. Okay. So P versus NP, because this is a classical NP problem.
Okay.
Or there are always instances, assuming P is not equal to NP, that people don't know. There are no known, in the worst case, polynomial algorithms. Okay.
Okay.
But that's why I said, therefore, there are, for which it can be exponential. I mean, assuming P is not equal to NP, then it means that it is unlikely to be a polynomial time algorithm for this. Yeah, correct. Because it's so that's why I carefully said that SAT solvers are so because they work so well in practice, because there are lots of islands of tractability. Okay, in applications in which you get formulas, you only see formulas that are inside these tractable islands, and that's why. And these heuristics are that people have engineered into SAT solvers are quite so good, okay, that they are able. But you can always find very small problems for which you can stump SAT solvers. And in the slide, I have this thing called pigeonhole problem. Okay, that is one very small instance which you can look at the thing, and that will be part of the first exercise that you will be typing into Z3. That very quickly becomes intractable. Okay. So.
Okay. Yeah.
Okay. Any other questions? So I'm going much slower than usual because we have a small class, and I see there are a lot of people that have not had logic background, and therefore I will go slow. Okay. So if you're uncomfortable with any even the notation, or please, this is the time to stop me and ask questions so that you will become well acquainted with. So let's start a predicate logic motivation. So for every, so here are some of the things that you cannot express in simple propositional logic, which only has propositional, the atomic things are propositional statements. Okay? So, for example, for every X, if X is a student, then there is some instructor Y such that X is younger than Y, something like that. Things like not all birds can fly. Here, there are several things that are concepts that are needed in order to have, make a language that can expressive enough to describe these kinds of things. First one is that here the objects are drawn from multiple sorts, types, or domains. These are all used interchangeably. Here, for example, we say student. Okay, that X is a student. Students, the set of students is a domain. Okay, here, instructors, birds, and I also have numbers. Okay, and those kinds of animals that can fly. Okay, these are all different sorts. And as somebody earlier observed, some of these domains can have an infinite number of elements as well. Okay, so so that is permissible. The language then has predicates and functions. For example, in this case, we need to be able to say that any X is a student. X means maybe a person, okay, is a student, not a student, and I stand for instructor. So the same entity can be a student but not instructor, and vice versa. Therefore, in order to distinguish between those domains, you need some predicates that take. Predicates are really functions, okay, or they are relations, okay, unary relations, so over these over certain domains. And you can also have age, for example. A stands for age. So since we want to compare the age of two elements in the domain, so this is a function that maps an element from one domain to another domain. Okay. So your language need to have predicates and functions, which was not allowed in predicate prepositional logic. We need a language that has quantifiers ranging over the domains that are a part of the language. And to say something like, for every X something holds, or there exists an X which satisfies some property, and so on. These are the three things that are not there in propositional logic that predicate logic introduces. Okay. So for example, the first statement can be encoded using this formula. So for every X, and for every X, my universal domain is maybe people, okay? So if S of X, that is, if he or she is a student, then there exists a person who's an instructor such that the age of student, the age of the instructor is greater than the age of student. So you could state things like this. So where you have not just proposition values, but you have predicates and terms that are constructed out of these functions and this. This, not all birds can fly, can be expressed in this way, that for all X, it's not the case that for all X, if it's a bird, then that it can fly. That means that can also be expressed as using existential quantification. It means that there exists some element for which, for some bird, for which fx is not true. So here it's first order, because the quantification, the restriction that imposes the quantification cannot be done over functions and predicates, all on these domains. Okay, so you can only, these variables that are quantified have to be ranging over the domains, okay, that we make it as part of the language, okay? And they can only be ranging over the first order elements, that is, elements belong to those domains, not over functions. For example, I cannot be quantifying for all predicates I, blah, blah, blah. Okay, so that kind of thing. That's higher order logic. So what will be, so using only first order logic and all our SMT solvers, which will handle first order fragments of first order predicate logic. So this is where I end. Okay, so this set of slides also has QBF, quantified Boolean formula, but I'm not going to be talking about that, because since I'm going to be introducing first order predicate logic, multi-sorted first order predicate logic anyway. So, and quantified Boolean formulas are a special instance of it, and therefore I will straight away go to this one. Okay, so here I should acknowledge this set of slides that I used are actually the original version of it was used by one Clark Barrett, who's the architect of one of the SMT solvers that I had listed earlier in the introduction lecture, CVC4. Okay, and I liked it because, you know, if I have to introduce it in 1 or 2 lectures, you know, this is a very compact things. And of course, I have, and with his permission, I've been using it, and I've also edited it several times to fix, you know, in various ways to, and also fix certain subtle issues. Okay, so I acknowledge his authorship. Yeah, so this is already I've stated. The language for the propositional logic, which is also Boolean logic, it only has propositional variables. Here you have more complicated expressions involving constant, function, predicate symbols, and so on. You know, things like this. Okay, so and it can also have equality over you know, functional terms and predicates, some which are less than, and equality is also a special kind of. So as before, I will introduce it by introducing the semantics and, I mean, sorry, the syntax and semantics, okay? So with propositional logic, expressions in first order law, I mean, yeah, they you know, they have a set of symbols, but here the symbols are logical symbols. They include logical symbols that you've already seen, which are as part of propositional logic, but also have some non-logical symbols, sometimes called parameters, non-logical parameters. Okay, and they like these functions, predicates, etc. They need to be given special additional meaning as well when you describe the semantics. Okay, and in the case of syntax, application, I mean, using those predicates and function symbols, will have to obey appropriate syntactic rules. Okay, so there is logical symbols. Okay, so which are the usual logical symbols, and then there are variables. So here, once again, we only finite set of variables because we are dealing with finite, you know, because we are only dealing with finite formulas, but you can have as large a formula as you wish to construct. Okay, but these variables here earlier, as you see, were only proposition variables, but here they can range over the domains. Okay, that are defined as part of the semantics, which are while assigning meanings to the formulas, and then it can also include quantifiers. The logical symbols or the non-logical symbols, these are logical because they have standard meanings regardless of you know, different models. Okay, whereas the non-logical symbols, we assume that we always have equality. Okay, although you can have predicate logic without equality, and the predicate symbols, there are constant symbols. These are, you can say that these are like null array. Okay, functions or predicates, and then there are function symbols. And sometimes, you know, the arity, this notation, if it's used in these slides, the arity is made explicit by showing it. So in this case, it says that plus is a binary function. Yeah, so these are first order long. Yeah, so first order long language must specify what its non-logical symbols are. And once you have these predicates and functions, you have to specify their arity and so on. So here are some examples. Of course, propositional logic is also a first order logic, but it does not have any you know, non-logical symbols. It only has predicate symbols, that is like constants, I mean, which can take either 1 or 0. So you cannot have predicates that are really functions, okay, that are related. Yeah? I mean, here is another, I mean, okay, this one says it is set theory. If some of you are familiar with set theory, this has nothing to do with the classical set theory or anything. Just say some other, first order language that has equality, some membership symbol inside set, and starting the constant symbol, which could denote an empty set, okay, and no function symbol. So number theory can have equality, then less than, which is strict inequality, maybe interpreted as strict inequality, a constant symbol 0, and some operations like successor, addition, multiplication, and exponentiation. Okay. So first order terms. Okay. So in defining now, so first we have to define, given these, the language, okay? I mean, these are the nuts and bolts of the language. These are just the symbols that make up the language, okay? Starting with symbols, then you use the symbols to construct other elements of that language. And finally, you build formulas, okay? Just like you started with propositional symbols, propositional variables, and propositional logic, and the constants 1 and 0. And then you had these rules for constructing in bigger and bigger formulas using the logical connectives. So here we start, since we have function symbols and predicate symbols, so you have to first define what are called terms, okay? Yeah. So I guess for some of you who have gone through logic, this could be a little bit boring, okay? But I hope, you will bear with me, and this will be useful. For the couple of people that have not done logic, how are you, is this pace good enough?
Yes, sir.
Okay.
Yes, sir. I think it's fine.
So term. So here, Clark has chosen to use kind of a recursive an operator for constructing the terms in the language, and then similarly we'll introduces building an operator to build formulas. So from atomic formulas. Okay. So here is this F, which is the term building operator. Okay. So given a function symbol F with additive n, you can construct a term with F at its root by applying that function F to a sequence of terms, alpha 1 to alpha n, one for each of the arguments. Okay, so that's what this thing says. Okay, so you can then start with. So how do you start this? This is how, given a bunch of terms, if you're an n-arity function symbol, it will build that, and that a function symbol can be either a predicate symbol or function symbol can be a predicate also. So these are the terms. So how do you start this? So the set of terms here, there is something called freely generated. It's kind of a technical, I call it mumbo jumbo. All it says is you say something is freely generated from the set of variables and constant symbols. All it means is you start with all the variables and the constant symbols are my starting terms. After that, you could use the other function and predicate symbols there to construct and to repeatedly. Freely generated means you can apply this function constructing terms a finite number of times, and anything here that produces is also a term in the language. That's all it means. A fancy way of saying freely generated from a set of variables just means that you repeatedly apply one or more zero or more times these things, and everything that you get is also a term. Okay. So far clear? Okay.
Sir, like I didn't exactly get what is it or
Yeah.
like,
Okay.
what does it look like?
So let's look at this. So concentrate on this portion in the thing that I have. Okay. So that I highlighted just now. I've said semantics of terms, but only look at this. Okay. Let's suppose that you had this example, which had these function symbols.
Yeah.
So here are some terms that I have constructed. So 0 is a term because it's a constant symbol. Right? So what
Right.
yeah, and then you can apply any function symbol. Here, successor has additive of 1. Therefore, successor of 0 is a term. Successor of 0 is also a term. And then plus is the binary operator, I'm assuming. So plus applied to those two terms is also a term. That's all. Yeah, that's all that thing says. Okay.
Okay.
So anything.
Just to be clear, in this model, like 2 and 1 does not
We
exist,
haven't
right?
introduced model yet. Okay. In this, yes, in this language. Okay, put it that way.
In this language, yeah.
Yes, yeah. What were you saying in this language?
2 and 1 actually does not exist, right?
That's why. So 2 and 1, 2, yeah, they're not there. That's why ignore this, the right side of the thing. Okay. So
Okay.
I will use the same example to do.
Just for intuition, I guess, yeah.
So I'm just, this part is only where it is turned. Yes, you're right. 2, 3 are not there. Okay. So you can't have them, correct? You can have this term is less than, 0 is less than this. Okay. Successor 0 plus successor 0 is less than 0. Okay, which is allowed. But of course, we'll get to predicate symbols pretty soon. Okay, I'm just introducing non-predicate terms here. Yeah.
Okay.
Okay. So what is an atomic formula? The predicate terms is also, I already said a predicate can be viewed as a function symbol as well. I mean, syntactically, but I'm introducing that as an atomic formula, okay? Because we will see that the meaning that is given to a predicate term will be the truth value, true or false, okay? So that's why, we are making that to be an atomic formula. But as far as its construction is concerned, it still is like a term. So what is an atomic formula? In propositional logic, you're starting with propositional symbols. Okay, there were no terms. Okay, and there were no predicates. So here is So if P is a predicate symbol in your language, then P applied to any terms, okay, that you construct. And P, assuming that it has with the right arity, and T1, Tn are terms as they're constructed, then that predicate term is an atomic formula for every predicate symbol in the language. So for example, that's what I meant. So for example, here you can have that's an atomic formula, okay, in that language, the number theory language that I just now introduced. Yeah. Yeah, if the language includes equality
Yeah.
symbol, yeah, question?
No, I get it. Yeah.
Yeah,
Fine.
okay. So then you can equality, when you replace P with equality, that's also a good thing. And you can have any other predicate symbol in that, that is included as part of the symbols for the language. So now what are the other formulas? The other formulas are constructed recursively from smaller formulas. You then use various logical connectives starting from the atomic formulas, and this formula building operator is introduced here as epsilon here. So it takes a logical connective and a sub formula, a smaller formula, and constructs a bigger formula by telling you how to apply that logical, the logical symbol to it. So P is a non-logical symbol. So the application of non-logical symbol, which is a predicate symbol, is what is used for making an atomic formula. So negation, given any formula, you can negate it by putting the negation operator. Implication, similarly. And this one constructs a formula, a quantified formula. So this one, given, assuming that all our variables are indexed, a finite number of variables are indexed from 1 through some max number. So it can, put the for all operator with BI and have alpha as the body of that thing. So as you can see that only for all is introduced, but the assumption is that exists can be defined this way, okay, as a derived operator. Exists V some alpha can be defined as negation for all V of not of alpha. Now this is possible. I mean, you can do this in classical logic. Okay, so as I mentioned in the last time, that we stick to classical logic. Okay, and then so that's why we assume that we define, once we define negation and for all, we get exists also. Okay? But exists will be defined as a derived operator, shown as. So it's 447. Okay? So let me see where I can start. I think I should. So formula examples, I will see, and then I will. Yeah. So after this slide, I will stop and take questions. So some examples of formulas. So in that language of elementary number theory, here, that is shown here. So the question is, which of the following are well-formed terms? That is, a term is said to be well-formed if it is constructed as per the rules of the thing. So is V6 a well-formed term?
Yes.
Yeah, because it's a simple variable. V2 plus V3.
Is plus considered plus considered a predicate?
No, why is there confusion here? It's very much says a function symbols.
Yeah. Then it is a valid term.
Yeah, but in this, yeah, but whether it is a predicate symbol or function symbol really doesn't matter right now. Okay, so I'm only saying it's a term. Okay, so yeah, well, okay. So I guess you're right. So we only define terms as having function symbols, not a predicate. Okay, So because if you apply predicate, it would be defined as a atomic formula.
Atomic.
Yeah, good.
Yeah.
P1 and P2. Yeah, as per a definition of terms, no. That's because this is a logically connective, and so this gives a formula and not a term. We have made a clear distinction between formulas and terms. Okay, because when you assign meaning, terms will have take on values from some domain. Okay, as opposed to formulas which are given truth values. That's how the semantics, formal semantics is defined. And that's why we make a distinction between, in the language, in the linguistic thing, this terms and formulas, because it's a formula, but not a term. Is that clear? Okay, I consider that as a yes. So atomic formulas. So are these atomic formulas here? This one. First of all, is this a well-formed formula?
Sir, what does that is that power like B1
Yeah, that's the
plus
exponentiation operator. I'm abusing the notation. Okay, so so consider this as exp operator, which is considered as a binary operator, which takes the base and the exponent. Okay, as two arguments. So yes, this is I'm asking the question if it's a well-formed formula, but it's not an.
it looks like
It is an atomic formula. Okay, because equality is a predicate symbol, which is applied to two terms. That's how we define
yes.
as an atomic formula. Yeah.
Yes.
Predicate symbol applied to terms is what makes an atomic formula, okay, without the usual logical connectives. Oh. So how about this one? This one is not, because this is now has a logical connective. Huh?
This is not atomic, like this would be a formula.
Yes, that is a non-atomic formula. So this one is
Yes, it is.
yeah, this is a mistake here. This is, I'm asking if it's a well-formed formula.
Yeah, like
It is a well-formed formula. It's a well-formed non-atomic formula.
yeah.
This one,
Like, wouldn't this be a term?
correct. It's a term and not a. So it's, well, it's not a formula. That's why it's not well-formed. How about this one?
I mean, this looks like it would be a
Yeah,
formula.
because this is very much a formula, the body portion, and it is. Yeah, this is something free and bound variables. The last slide that I will use, and I will start with semantics in the next thing. So this defines what it means for a variable to occur free or bound. So it's applicable to formulas that have, for any formula, for example. So a variable x is said to occur free in a well-formed formula alpha. If alpha is an atomic formula, then x, any variable that occurs inside it, an atomic formula, remember that it cannot have any quantifiers. Okay, quantifier is a logical connector. Okay, so every variable that appears in that is considered to be free. So if you only do negation if it is free in alpha, then so it is not alpha. Similarly, implication. So the boundness comes only when you're using quantifiers. Okay. So if you have a formula constructed with the universal quantification of a particular variable vi, then it occurs every variable that is not vi is said to occur free in this whole formula, in this quantified formula. But vi itself is considered to be bound. Okay, vi is said to be bound in this formula, in this entire formula. Okay, so for example, and you will see why this is thing. So where is it? Stop here. So no. So let's take this one. Okay. So for example, in this sub formula here that I've highlighted, is x1 free? Not the entire formula. I'm just using this sub formula. X1 is, it's getting late, so I will answer. So X1 is free because there's no quantifier that actually is within its scope. Okay. I'm only considering this strict sub formula. So in this, and here X3 in this in the sub formula, X3 is said to be is bound. X3 is bound. X1 and X2 are free. So here X2 and X3 are bound because they are bound. There are quantifiers that bind them, but X1 is still free. And in this, every variable is bound. Okay, that's how it's the concept. Okay, so I will stop here, and yeah, next time I will start with semantics. So if there are no questions, I'd like, if there are no questions, I'll stop sharing. Are there any questions?
Sir, you had given an exercise like, will it be available in Moodle or something?
Well, I will make the exercise. Okay. Oh,
okay.
You could if you want to start. No. I've already uploaded the slides for the propositional part. Okay, and you can actually start working on modeling those constraints. Okay, of eight queens and Sudoku. Okay, in that order. So, and then the first assignment will be modeling those things and then running them, checking them in using Z3. So Z3 demo, I'm hoping I will give next Monday. So starting next week, it will be Monday, Wednesday. Okay.
Okay.
At 3:30. So if you want to get started and get a head start, that's what the assignment will be. So you can look at the slides and start working.
Okay.
Yeah. So if there are no questions, I ask the students in the class to drop off, and I want Madhukar and Diganta to hang on. If they're still there.
Yes, yes, sir, I'm here.
Yeah.
Thank you, sir.
Okay.